CPU scheduling refers to the short-term scheduling of ready processes to run on CPU cores. This type of scheduling is needed for multi-programming systems, and it provides a way for the operating system to share CPU resources among multiple processes. In order to implement CPU scheduling effectively, a number of competing objectives must be balanced within the system. For effective system utilization, the scheduler must keep the CPU busy performing useful work. In other words, CPU throughput must be maximized. We don't want the CPU to be idle when processes are waiting to run. For process performance, we want the CPU scheduler to minimize the amount of time a process must wait to begin executing. Furthermore, we would like to minimize the total round-trip time from the moment a process is started to the instant it completes. Finally, with user-facing systems, we want to maintain system responsiveness. If a system seems unresponsive to a user, the user might reset the system, potentially resulting in data loss. The key to making effective scheduling decisions is to understand the behavior of typical processes in the system. In general, processes are either executing on the CPU or they are waiting for I/O operations to complete. While a process is waiting for I/O, there is no need for that process to be assigned to a CPU core, since it will not be able to make forward progress until the I/O operation has completed. Since I/O devices tend to be several orders of magnitude slower than the CPU, other processes could enter and leave the CPU before the I/O completes. Thus, by yielding the CPU whenever a process is waiting for I/O, CPU resources are more effectively distributed among multiple processes. Processes may be classified according to whether they perform more computation than I/O, or more I/O than computation. This distinction is relative and depends upon the system under discourse. However, in general, a compute-bound process spends the vast majority of its life cycle performing computations on the CPU. These processes tend to load some data into memory and then perform extensive operations on that data. At the opposite extreme, processes may be I/O bound, in which case they spend the majority of their life cycles reading or writing data. The amount of computation performed by I/O-bound processes is relatively minimal. As such, they tend to require CPU resources primarily to arrange for device I/O operations. In general, interactive processes may be considered I/O-bound since they spend the majority of their life cycles waiting on the user, who might or might not even be sitting at the keyboard. In order to share CPU resources among different processes, the scheduler may be designed to be either non-preemptive or preemptive. In a non-preemptive scheduler, a process runs until it voluntarily yields the CPU, either by an explicit yield system call or by requesting I/O. This type of scheduler has low overhead and is good for I/O-bound processes. However, a single compute-bound process could hog the system and prevent other processes running. When processes might become CPU-bound on a multi-programming system, a preemptive scheduler is used. This type of scheduler is more complex to implement and has higher scheduling overheads, but it more effectively shares CPU resources by interrupting long-running processes, removing them from execution, and scheduling other processes to run. One of the concerns of CPU scheduler design is that of fairness. A fair scheduling algorithm gives equal CPU time to all processes on the system. In general, this fairness implies that every consumer on a system receives an equal share of resources. In most cases, however, it is desirable to design a scheduler to be unfair. On interactive systems, the human user tends to prefer that foreground processes are more responsive to requests than our out-of-sight background processes. When systems are shared between different classes of user, one class of users might be considered to be more important than another class of users, and their jobs may be given priority in the system. Scheduling priority is the general mechanism by which unfairness is implemented in a scheduling system. In a priority-based scheduling arrangement, processes may be given unequal shares of the CPU. Higher priority processes are given a greater share of the CPU, while lower priority processes are given a lesser share. It should be noted that a higher priority in a scheduling system generally correlates to a lower priority number. Thus, a process with a priority of 5 has a higher scheduling priority than a process with a priority of 25. The process with the lower priority number receives a greater share of system resources. Priorities in a system must be carefully adjusted to prevent starvation and thrashing. If higher priority processes are always scheduled over lower priority processes, the lower priority processes will starve. In other words, they will not run for an extended period of time, if ever. At the opposite extreme, if the system switches too frequently between processes, the operating system will spend more time managing and scheduling processes than the processes will spend running. This situation, known as thrashing, is bad for system throughput. The scheduling algorithm used in CPU scheduling must strike a balance between these extremes, preventing starvation while avoiding thrashing. Most scheduling algorithms can be tuned to match the specific requirements of the system. In addition, some operating systems, such as Linux, provide multiple different scheduling algorithms that can be selected by the system administrator. The choice of algorithm and the tuning of an algorithm to adjust various parameters are part of system policy. Scheduling policies are set by the administrator to adjust resource sharing decisions, enabling prioritization of different processes or users.